Good morning, everybody. Here's 10 o'clock in Taiwan. Welcome to this morning session. The lecture will be given by Professor Jiuhou of the University of Science and Technology of China in Hefei, China. The topic is multi-scale ionospheric variations reviewed with Beidou geostationary orbit stabilized. This is a part of the low latitude ionospheric research working group lecture series, and so we're very happy to have Professor Lei to give a talk on this very interesting topic. But before he starts his talk, I want to introduce to you about him a little bit. He got his bachelor degree from Hunan Normal University in China, and then went to Beijing to study at the Chinese Academy of Sciences. I suppose this must be later he might tell us having to do with the National Space Science Center. And he got his PhD in 2005. And after that, he went on to work as a postdoc for 3 years in Anchor, in Boulder, Colorado, United States. And after Anchor, he went to the Aerospace Engineering Science Department of the University of Colorado for another 3 years. And since 2011, he returned to China to work as a faculty at the University of Science and Technology of China, at the School of Earth and Space Sciences. And some of you might have followed the news that in April, his university, namely his school, has organized a very big meeting in space science and technology, reporting on many exciting programs in near future. And I think that Professor Lai is not going to talk about some of the things reported at the meeting, but then concerning the ionospheric physics, he will give us what he knows, give the most advanced knowledge in this field. Professor Lai, please go ahead.
Okay, thanks Professor Wing for your invitation, and also so thanks for all of you for coming. So good morning, good evening, maybe good afternoon, depending on where you are. Okay, today I will talk about the multi-scale ionosphere variation from the Beidou geosynchronous orbit. Okay, first credit should be go to my 2 students and Dr. Fang, and the other PhD student, Mr. Wang. And I guess you all very learn about the space weather effect on the global navigation satellite system called GNS. There are many ways to affect the GNS system. First of all, we know the solar radio burst will cause the interference of the frequency interference of the satellite. On the other hand, the space weather event can cause the ionosphere change, include the background, and also for example, we always see this kind of like cloud feature in the plasma, and we call the plasma irregularity. And this kind of depletion or the ionosphere irregularity will cause sometimes the loss of satellite track. And because the ionosphere we know is a dispersive media, so the reflection is vary with the frequency. So for use different frequency, we can get called ionosphere electron along the path we call the total electron contact. So So if we use a dual frequency, for example, different systems, GPS and Beidou, GEO-RAC and other systems, and in this way we can calculate the range error and the phase difference or the range difference. In this way, we can calculate the ionosphere density or the ionosphere total electron content. We call the TEC. We know there are many GNS systems, and for such as the GPS, GEO-RAC, and Galileo. And in this talk, we mainly focus on the Beidou system, and there's some unique feature I will talk later. And for the Chinese Beidou system, currently they are similar besides the MEO satellite, and there has the geosynchronous satellite called GEO satellite and inclined geosynchronous satellite. This is really a unique feature, and the satellite can observe the TC around especially in the Asian region, and without change too much of for the ionosphere peace point. I will show the later. And this slide shows the comparison of the called ionosphere peace point, and as a function of the latitude and the longitude for two kinds of satellite. One is for the non-geo satellite, for example, GPS and Galileo and other, and also some of the non-geo satellite from Beidou system. And the red panel shows the ionosphere peace point for the geo satellite. And you can see the very clear for the one particular station, you can see the IPP change significantly include the latitude from 35 to 15 and the longitude from 110 to 135. So you can see significant for the spatial change, even for one location. But for the geosatellite, you can see the peace point almost fixed. In this way, we can separate the influence of the include the spatial and the temporal variation. So this slide shows again for this station the unfade, and this is for the long geosatellite TEC. You can see as a function of the UT time. This is the daytime, and this is nighttime. This from the geo satellite. You can see these two kind of data sets show the similar trend, and from day and to night for the diurnal variation. But for the non-geo satellite, you can see the ionosphere called the TEC. You can see large scatter. That's associated with the not only the timing variation and also the spatial change. For the Beidou satellite, you can see the TEC for here I showed the four satellite from the geo satellite 1 to geo satellite 4. You can see for each curve, you can see the time that the temporal variation, and between of this each curve, you can see the spatial variation. That's called the longitude variation. As I showed for these four satellites, the longitude span about 10 degrees. That's about the spatial distance about 200 kilometers. You can see this is smaller, but sometimes I will show later there are large difference. We can use this data set, so you can see very clear and accurate to detect the time variation and also the spatial variation. So in this talk, I will include 4 parts. I will start with called the mesoscale ionosphere disturbance, and also the associated with the irregularity at the mid-latitude. And although these kinds of features is widely studied, for example, the mesoscale called MSTLD can observe by the air glow. You can see very clear feature. You can see the wavefront and the horizontal wavelength about a few hundred kilometers, and measured by the air glow different species for the atomic origin and other species, and it had different altitude from 97 to 250 kilometers. So in our university, we build air glow image around in mountain. That's the latitude about 33, and the longitude is 116 east longitude, and about 200 kilometers away from our campus. And we use this air glow, we can detect the MSTLD, and at the same time, we use the GPS satellite in this view and compare the MSTLD from both the air glow image show the top panel by the red line, and the GPS satellite for the board panel, you can see the occurrence for these kinds of lifetime mesoscale TLD. You can see the in center channel, you can see the maximum occurrence takes place around in summer, June and July. And these two kind of observations are very consistent from the AOGS and from the GPS. And usually we for the MSTLD suggest caused by associated with the low atmosphere, especially for the gravity forces. So we use the AOGS image. We can measure the green line, and at 97 kilometer, we also plot the occurrence frequency at the same wavelength for MSTLD, and but for the from the green line, you can see the occurrence doesn't match with the from the AOGS or the GPS satellite. That means for the mid-latitude lifetime mesoscale MSTLD, a lot associated with the low atmosphere, for example, the gravity wave, and common suggest. We also further compare the statistical results for include the period, phase speed, and amplitude, and wavelength, and the left panel for the AOGS and the right panel from the GPS. And generally, they are consistent, include the period around 1 hour, and the phase speed about 100 meters per second and a little bit low, and the amplitude about 10%, for the wavelength about 200 or 300 kilometers. But if you look at the closely active for the period, there are some different. For example, for the AOGS image, the period around less than 1 hour. For the from the GPS acting around 1.2 or a little bit larger. So what causes this difference? So we think about there are two issues of detect the MST from the GPS and for the non-GEO satellite. And we learn for the AOGS image, we can detect the wavefront and the wavelength accurately. But from the non-GEO satellite, for example, GPS satellite, for the APP, you can see the location change significantly. I already mentioned in the a few minutes ago, and you can see the latitude and the longitude. And in order to remove the background, we need to fit in the observation as a function of the longitude. So this remove the background and then get the residual and can get the wavelength feature. That's called MSTLD. And there are two issues. One is the background, how many orders, how to remove this background. So it's an issue. Another one, when we look at the waves, and because the satellite move around at the function of the latitude and the longitude, they automatically will cause the Doppler shift for the, especially for the period and detection. So we build a network in Anhui around our campus, and very dense network. You can see there are 4 stations, and Munchen, Benpo, and Fala, and Hefei around our campus. Another is a little bit far for Yellow Mountain. And we took this data set. For example, we use this 4 station. Is very close for, you can see the distance for the closest distance about 60 kilometers, the largest distance around 110 kilometers. So it's very good for study for the MSTLD. So for the GEO satellite, we don't have this kind of issue for the need fitting the data as a function of the latitude and the longitude. We just remove the background very easily. We can get the MSTLD feature and also detect the period. And then we can compare this feature for example, the period, velocity, and wavelength. We just draw your attention to just look at the period. You can see this for the AOGS, we can consider this the truth, and then compare from the GEO satellite and from the GPS satellite. You can see, as I mentioned before, the GPS satellite usually give larger period, about 20 minutes longer or even more. And for the Beidou satellite, you can by the red line, red dot, you can see always close to the AOGS image. So if you do further do the correlation, this from the GEO satellite and do the correlation is much close compared to the GPS satellite. That's because we have for the GEO satellite without this kind of, for example, the Doppler shift and also background issues. That's really important for the wave detection for the MSTLD. So we also for the to use this network to, because for the GPS observation, for the GNS observation, for the Beidou system, we can observe the ionosphere for 24 hours per day and 7 days per week. So it's very good to detect for the occurrence of the MSTD. This shows the 2 years data as a function of the log time or UT, and also the months. This one 2016 and 17 as a function of the log time. You can see the MSTD. The majority you can see the occurrence in the latter time, and you can see the around the summer period. For the daytime, you can see around the winter period. So you can see two features: the daytime and the nighttime. They are different. One is in winter, another in the summer. So it's different. So we further use the geosatellite TC data. We can detect the propagation direction and also wavelength and the wave phase speed. And you can see for the latter time always propagate to the west south. That may be cause associated with the Parkinson instability, but for the daytime many propagate with southward. That may be associated with the gravity wave from the low atmosphere. So this from the geosatellite provide very good statistical result for the MSTD. And also we use the Beidou TC. Definitely you can also look at the, for example, the irregularity of the scintillation. And we use the TC data, we can provide very high accuracy of the data, the TC variation. And we can calculate called the ROTI that represent how the density fluctuation also to represent the ionospheric irregularity. And we use this data set and also do the statistical analysis for the mid-lateral irregularity. You can see at the same station and for the same tier, you can see very clear. For the latter time, you can see the irregularity and the MSTD just show a very good correlation. But for daytime, you can see the MSTD in winter, but you didn't see too much irregularity in the daytime. That may be associated with the density profile. But for the night time, you have large gradient, but the daytime is not such gradient is not allowed to develop for the, especially for the Parkinson instability and development. So this is for the mid-latitude periodic oscillation we call the MSTD. We also use this data set to can look at the ionosphere periodic structure at the low latitude. So this is really, this shows the raw data from the geosatellite. You can see very clear. You can see some fluctuation very easily, but this kind of feature is not easy to see from the non-geosatellite. And if we just remove the trend, you can see the oscillation and the period around 20 minutes around. So it's really see the coherence pattern from different stations around 23 and 20 degrees and different longitude. So if you do the statistical analysis, you can see this kind of compare the mid-latitude MST for this period oscillation. Many happened around the daytime from around 10 log time to 18 log time, and the period, as I mentioned, about 20 to 30 minutes. And also should show the preference of the season variation. You can see this is the 2 years data, and this is log time. You can see for the North Hemisphere, you can see around 12 December. That means for the winter season. And for the Southern Hemisphere, you can see in about June. So it's also in the local winter. So this is somehow tell the mechanism. And we also look at take the observation from the Asian longitude sector from 20 south to 30 north. You can plot as a function of the latitude. You can see the for the magnitude, absolute magnitude or the relative amplitude. Both you can see the larger occurrence around 15 latitude and 20 log time. That's around called magnetic, called equatorial anomaly region. So this somehow associated with maybe associated with the low atmosphere dynamic process, for example, electron field. So at this point, we don't know exactly. But if we plot the occurrence as a function of the latitude and the longitude, again, you can see the large amplitude occurrence around this equatorial anomaly region. That may be associated with the stratosphere gravity wave and usually occurred in the winter season. But we need more, for example, the data set and also from the low atmosphere, and also we need a theoretical modeling to see whether these have some correlation or the cause and effect relationship. So this is for the theoretical observation. And we also took this data set to look at the diurnal evaluation. We look for the typical diurnal evaluation, for example, you have see the high density in daytime and low density in nighttime because we have the solar radiation or the ionization in daytime, but as the solar radiation is gone, we don't have the solar irradiation and the ionization, so the density is low. But sometimes we will see the very different pattern. For example, the same station, but for the different day, you can see the daytime, you can see you can see the large density and then drop and then raise up again. We call this like bad out feature, like you can see apple and bad and the density depletion. And if you look at the nighttime, you can see density depletion, and then you can see increase again, but it's not usually we see the high density in daytime and continuous decay from daytime to nighttime. So you can see this called the bad out and the nighttime enhancement. So this GEO satellite you can see very clear, and also you can detect very small and depletion or the enhancement. We take advantage of this set and use the data, the chain from in the Asian region from the about north hemisphere 40 degrees to about 30 in the south hemisphere. We can do the latitude and also the seasonal evaluation. This shows the occurrence of the called the daytime TC bad out. That means the daytime have the depletion of the density. And this occurrence as a function of the month, and this for the occurrence you can see from the mid-latitude in north hemisphere and also the north hemisphere crest region for the equatorial and also the equator region and all the south hemisphere. You can see because it's a high occurrence in the north hemisphere mid-latitude and become low occurrence in the equatorial region, especially for the crest region, and then goes up again at the equator. And you can see for the south hemisphere in the mid-latitude, you also see the high occurrence again. So you can see the also for the in terms of the season, you can see the larger occurrence in the for the June season, not for the northern hemisphere is local summer, for the southern hemisphere local winter. So that's somehow related to the season, related to months rather than the season relation. So what's the cause? So we also did some further analysis, but we will not go to the detail. And on the other hand, we also use this unique data set to detect the nighttime enhancement as a function of the latitude. You can see show different station. You can see for the mid-latitude, you didn't see too much nighttime enhancement signal here, and then you can see the mid-latitude enhancement, and you can see the called irregularity of the fluctuation, and again you can see how the change with the latitude. If we plot the data as a function latitude and local time, you can see these two equatorial anomaly, and then you see the enhancement. For this enhancement seems you can see first see at high or mid latitude and then extend to the low latitude. And from the data set, we divide with this kind of enhancement different category. For example, as showed from the extent from the north hemisphere, or just the equatorial region, or the extent from the south hemisphere, and so on. So we have different features, and but you can see the very clear, and even the magnitude of few TC, and can detect very easily from the GEO satellite. So we also again we can look at the occurrence and how vary with the season and also the geomagnetic condition. And this for all the data set, you can see more often see this kind of nighttime enhancement in the March and September. That means the equinox season. And for both for the quiet time and the store time, but definitely for the store time, we don't have too much data set. And for the, but it's still again, you can see for the occurrence days, it's much more for the quiet time, but the occurrence rate may be similar, but we didn't see too much the geomagnetic activity dependence from the, in terms of the, this kind of seasonal valuation of the occurrence. And we also took the data set from the ionosound, include the peak density and also the peak height. So it can indicate some of the information of the equatorial dynamic of the ionosphere. When you see this kind of enhancement, you always see the enhancement of the peak height and the vertical height from the ionosound. That indicate maybe this associated with the called the free reverse enhancement of the electron field, the eastward electron field enhancement, and essentially for the low latitude. But the wind and also the neutral wind and the composition definitely have some modulation and contribution. That's from the for the periodical for the temporal variation. We have the, for example, MSTLD and the periodical oscillation at the low latitude and bad out and nighttime enhancement, all from the time variation point of view. That's for the temporal variation. For this, as I mentioned, for the geosat for the Beidou system, we have the very unique, and we have the geosynchronous satellite. And we look for the previous major study to focus on the ionosphere vary with longitude, especially for the low latitude equatorial anomaly. At that time, it was reported their waveform structure that's associated with the non-magnetite origin from the low atmosphere. And for the magnitude for the TC around 2 TC unit and the function, for example, for the different longitude and the function longitude and the depletion and the enhancement. And also some report will show the longitude variation, for example, east and west of the America and Africa and also the South America longitude, even in the Asian longitude. But we should ask whether we can see this kind of longitude structure even in a small region, for example, from county to county, whether the ionosphere are the same or see the significant difference. So we took the opportunity from the Beidou geosatellite network. For example, we have 4 geosatellites. Actually, we have 7. We just show 4 satellites. You can see for each station we have observed for the 4 satellites. You can see the distance of each of these satellites about 200 kilometers. So we can detect very fine structure, a small regional evaluation of the ionosphere. But usually we see from different satellites that ionosphere are similar. That's expect because the longitude variation about 10 degrees, that's around the 10,000 kilometer distance. The ionosphere should be different for different from the different geosatellite. But for example, this from the 2016 and March 8th, and then 3 days later, you can see for the same station, you can see the density, the TC from the maximum from 20 TC unit go to 80 TC unit. So significant change about by a factor, actually the TC about a factor 2. That's even small regional, only around 1,000 kilometer distance, or the from the, for example, 2 or 3 or 200 kilometer, even you can see the very, very large TC or the ionosphere change. That's a very new phenomenon. And we also do the occurrence to see how often this kind of larger gradient or the fan structure occurred. So this is the observation days, almost for the satellite, for the GNS observation, almost every day we have the observation. We have the 30 days for each month, And for the event, you can see for the burst happened around again in March and September, and a little bit in the December. So you can see the semi-annual variation. The occurrence is not low. If turned out a 5 TEC unit between each station, you can see the occurrence go as high as 60%. That's very high. So it's not a rare phenomenon. It's usually often happen. So this further showed one particular event. So this from the 2021 and March 31 at the event. So this plot the fixed log time from the Beidou chain from north hemisphere to south hemisphere. You can see even at the same log time, you can see the TC change significant. You can see from the 40 TC go to 70 TC unit, see a significant change, only a few degrees distant. And if plot the gradient, and we plot, for example, 1 TC degree, that 1 TC 100 kilometer to 60 TC per 100 kilometer, you can see, especially in the equatorial anomaly region, you can see very large gradient. And you can see the east side and the west side show the different sign. For example, this for the westward larger than the eastward, and this for the westward less than eastward. So you can see the transition in this longitude. But what caused this fan structure? So we took the this is the movie you can see more clearly for different log time, and this is the 12 log time and 1 o'clock, and you can see the 14 log time. You can see the dependent log time, and but major you can see the larger difference happen in the around the daytime, around for example from 11 to the 14 log time, when the TC or the ionosphere have larger magnitude. You can see the movie once again. You can see the TC low from morning, and a larger gradient you can see happen especially in this region. So we further take the outcome observation to see what's the cause for this larger gradient. And for example, this show one example. This for the TC I just show you, and these two orbit, and but for the same latitude at the same log time, because the log time shift is very small for these two log time. And we plot the vertical drift and also meridian wind, and you can see these two orbits, they definitely show some large difference, and for the velocity, vertical drift, and also the neutral wind. But we do when we plot the E cross B drift as a function of the day for two events, 2020 and 2021, and you can see the how they are match each other. You can see the red line for the TC eastward and westward asymmetry. We calculate the gradient, and the black line for the vertical drift different from the icon. You can see for two log time, you can see the day about maybe this majority from the noon, and this is the afternoon. You can see both show the correlation, and for this another event, you can see the jump and the down, and see this very good correlation. So maybe this tells us this kind of larger fan structure in the atmosphere may be associated with the longitude variation of the vertical drift. And we further also looked at wind, but it's not didn't see this kind of coherent pattern in the wind data. So, but definitely we need more data and also the modeling to answer this question: why there is a larger difference in this in the Asian region, and why the wind and has not large effect, but the vertical drift is a major play a major role. So what causes this kind of electric field change? Because the magnetic configuration or other mechanism, we need further investigation. So this is further. So we go to the final conclusion for the summary. I should say the Beidou geosatellite ionosphere observation provide a very good fidelity observation, especially to study the multi-scale ionosphere variation. So in this talk, we talk about the meso scale, about the period about 1 hour, and the spatial variation about 3 or 200 kilometers. And for also even for the small scale, the ionosphere equality, and for other periodic observation, and also ionosphere at the larger scale, for example, bad out and even the lifetime enhancement. We also look at the MSTD and ionosphere equality relationship at the mid-latitude. We found that there is a close relationship between the MSTD and ionosphere equality at the lifetime at the mid-latitude, but didn't see this kind of correlation or relation in daytime. That may tell the mechanism may be different, and for the lifetime just maybe initiate in the ionosphere, but for the daytime MSTD may be associated with the low atmosphere forces. So we also look not only mid-latitude, we also use this data set to study the daytime ionosphere periodic oscillation of the structure at the low latitude, especially in the equatorial anomaly region. And the period about half hour, and maybe it's also similar like this kind of MSTD, but further work should be address this kind of issues. And besides this kind of temporal variation, and we also look at spatial, especially fan and ionosphere longitude structure is around 200 kilometer distant for each, for example, geosatellite between these different satellites. So you can see small scale, like a county, between county and county, and see the ionosphere is sometimes is a very large difference. From the modeling perspective, we usually have the gradient, for example, 5 degrees, and that means about 500 kilometers, the ionosphere is the same. But from this observation tells that there are very large difference, even in around 200 kilometer distance in that same latitude. And the primary result we show the E cross B drift or the electric field maybe play a dominant role, but definitely we need more work to do to understand the underlying cause. And I think I give a very brief talk about from the geosatellite from Beidou system to for the Asian sector ionosphere variation. So I think I should stop here, and thanks for your attention. And I'd like to take some questions.
Yeah, thank you so much, Professor Lei. Any question from the audience? You could either just turn on your mic or write down on the chat box so for Professor Lei to read. And wait maybe 5 seconds. Oh, I do. Okay, that's just from the host. So let me ask one question, because you asked the question yourself, but maybe you might already have some answer or some idea.
Sure.
Lastly, you talk about which is the very strong localized eco-speed drift.
Right.
And what produced the electric field?
Yeah, that's the open question. Actually, from the icon observation, provide a unique this kind of data set, and unfortunately, the icon set already lost contract. And from the observation hertz, they are about, for example, the difference about 20 meters. Even for if you look at the longitude about less than 20 degrees, about 20 degrees, there's a lot different. So to respond to your question, but we don't know exactly whether the wind or the tomography or the magnetic configuration, for example, different angle and the decline angle or this kind of structure, we don't know at this point. So we need this is just a phenomenon. We see this kind of correlation, but we don't know exactly what caused this huge difference in the vertical drift or the electric field.
How high is the wind?
The wind should be, this is the wind. From the wind, actually, there are also large difference. So about for 20 or for 30 kilometer per second different, but just the pattern different. Just you ask a very good question, a useful question. Maybe although the wind doesn't show very, maybe I have a backslide to show the wind. This is the wind difference. You can see the wind can sometimes go to 40 meters per second and 45 meters per second. They are large difference. But the question is the issue that we didn't see this consistent pattern, and maybe the wind has some different and then further adjust by the other effect, for example, magnetic field strength and also the magnetic field configuration, and then further, and also the different region, for example, E region and F region in the ionosphere maybe have different contributions. So the wind effect may be very complicated, not just show the as a function of the longitude, and also the wind for the electric field actually integrated from the longitude along the field line, but not just the localized neutral wind produce the electric field. That may be a lot of work to do to address this kind of question, why the wind is not, how the wind effect and why the electric field shows this kind of larger spatial or the further localized variation. So that's my answer for the.
And it has nothing to do with the solar storm or solar events.
Yeah, that's a good question. Actually, we look at the many events. Most of the event is nothing to relate with the solar event. Actually, very quiet. And if you look at geomagnetic activity, KP index almost flat in this period, although some fluctuation, but it's not a large jump, very active period. So this is not, yeah. But for the stop time, we do see some of this kind of feature, but the majority see observed during the quiet time.
Okay, thank you. Now you talk about the Beidou satellites. How many Beidou satellites are there? You have 4, 5, 6, 7?
For the Beidou satellite, we have 45, but for the geostationary satellite, we have 7. But some of those, maybe the distance is very small. So we just took 5 or 4, let's go to the, we just took the 4 or 5 satellite for the geosatellite. Okay, maybe, yeah. We have 7 geosynchronous satellite and 9 inclined geosatellite, and that means like the 8 and so this is, but 2 of them, the location is very close. So we just choose 4 or 5 to look at this kind of small distance, the longitude about span about 10 degrees, and each of them about 200 kilometers. Just look at the very final or the localized variation of the atmosphere. But this is not easy to detect for the non-geosatellite because there is a larger fluctuation of the scattering due to the spatial variation. It's hard to tell. It's due to the longitude or the timing or the other latitude variation.
And someone in the audience may want to ask, are this data open to the public? I mean, someone else other than you want to look at the data. Is it possible?
Yeah, we have the network for a few stations, but in China we have many stations. For all network should be easy, should be available for everybody for the scientific study. We have 5, actually we have more, about 10 station data to provide for the users.
Yeah,
but
of course,
maybe from other data sets should be. Actually, we should have 100 stations to use the.
Right, that would be nice. Yeah.
Sure.
I hope it's not in the ocean. The purpose of the working group of this low latitude research and atmospheric research working group is to promote or to encourage data exchange and exchange of information. So if some of you are interested, in knowing more, or even to have access to data, as you have heard from Professor Lei, he welcomes you, to contact him. Yeah.
Sure, yeah, welcome to use this kind of data set to
especially for the researchers at the conjugate point of Hefei.
Yeah.
This is on the southern hemisphere of the 30 latitude degree.
Yeah. We actually we took some of the data set. For example, you do see some conjugate and data set in the south
Actually,
hemisphere.
is in the Indian Ocean.
Yeah.
or Malaysia, Indonesia.
Some continents and this island.
Okay, great. I think that this is a wonderful lecture, and I want to make an announcement that we will have 2 other lectures to be scheduled. One is on the International Meridian Circle project, and Professor Michelle Brown will give a talk to describe the project, which will be open to international cooperation, of course. And then another talk will be given by Dr. Ida Li of the Central Weather Bureau in Taipei, and he will also describe the space weather research program of his institute, and also he will describe how the archive data from Taiwan could be assessed. So please look forward. Please pay attention to the announcement, and we welcome you to this 2 lectures in future. And I want to thank Professor Lei again. 谢谢你啊，刘老师。Yeah.
Okay, thank you for all the audience. Okay, thanks. See you around.
I hope to see you in person next time.
Yeah,
Thank
see
you.
you. Thank you.